This production is brought to you by the University of Edinburgh.
Well, it's a great honour to speak here in Robin's memory. I'm actually going to take the converse tack to David and mainly speak about his science, and I hope something of the man will come through. I should mention, this isn't so accidental. David would, of course, have spoken about his science, and David originally had an hour, and then after Robin's sad death, we had to make do with the time resources we had. So David, I thank David very much for kindly just taking part of his time to speak about Amir. So Robin, I'd like to tell a little bit about his career and research, and I'll begin with various lists. And the first list is a list of how he spent his time, starting off at Ferranti. Actually, I might point out he never did do a PhD. He was quite proud of that. It's part of the pleasures of the British system at that time. Those days are long since gone. After Ferranti, doing practical things, he began to teach at City, and he met basically the British mafia in semantics, as you might say, the Bristol, London, Hudson Park, Scotland Strachey, and others as well. He also began to learn his craft and began to move from a teaching post. He went to his first research post in Swansea with David Cooper, where he worked on program schemata and program simulation. The paper on program simulation is still an important paper, and the title is An Algebraic View of Something. And he himself credits Peter Landon with that initial introduction to the algebraic point of view, which so influenced him basically for the rest of his life. Yes, indeed, for the rest of his life. Then he went to trip with David Cooper and met Zohar Mana, who David already mentioned. And through Zohar, he got a position in Stanford with John McCarthy, who wanted some program correctness work, and that resulted in the Stanford version of LCF, a kind of theorem-proving system for Scott's logic of computable functions. And there too he began his first thoughts on concurrency, and we'll come back to the ins and outs of that later on. But not everyone knows he'd already done quite a good deal of thinking already in Stanford and that. Coming to Edinburgh in '73, he did some work in semantics. I'll mention that. That's kind of important for theoretical orientation as much for its content. Continued his work on LCF. At that point, in order to move forward with LCF, he had the brilliant idea of combining it with an appropriate programming language. That was how ML was born, the MetaLanguage. That got further developed, of course. And then he moved away from that and, I mean, not entirely, but moved largely over to concurrency again, working on CCS, the calculus of communicating systems, and Aarhus is in parentheses with that because that's where he produced his first book on it. They were kind enough to give him the time to write and to speak. Then later on became the pi calculus, action structures. These are all a whole sequence of marvelous models of concurrency, one evolving from the other, eventually resulting in his final such model at Cambridge on bigraphs. And his final work, or his final thoughts, since it was never completely developed, it's just beginning to be developed quite actively. He had many plans at the time of his death. I was talking to him just a week or two before his death, and he had plans. He was working at, was giving lectures at Edinburgh here. He was actively involved with a group in Copenhagen, the ITU University in Copenhagen, and with workers elsewhere. And he had many particular projects in mind, as well as general point of view, and we've been sadly deprived of what that would be. All the same, he was extraordinarily well recognized during his lifetime, and deservedly so. And this is quite a long list. I guess one points out to the Turing Award, and he was a fellow of everything in sight. The Royal Society of London, Edinburgh one, Academia Europaea, National Academy of Engineering. He's a lot more honours, but I can only cram that much onto one slide. Many honorary degrees, many prizes. If we concentrate on his Turing Award, why did he get the Turing Award? Well, apparently he got it for 3 things, and the 4th thing wasn't bad either. So one was LCF, which we've already mentioned. One was ML, the MetaLanguage. One was CCS, the General Theory of Concurrency. This was 1991, so he had yet a good deal more to do on concurrency, and also his work on semantics. So, just to get a feeling for what are the proportions of, I don't know, output or achievement, I don't know, of work that he did in these various things. So if you look at just ratios from the books that he wrote, and you count definition of standard ML and revise as one book, they say 4 to 2 to 1. So 1 unit of LCF 2 units of standard ML and 4 units of concurrency. That's not an inappropriate way, at a kind of gross level of saying what he did in terms of where his contribution went. So I want to begin with a quick, so what I wanted to do was, rather than carry on giving lists, try to give a little bit of technicality here, a little bit of technicality there. And I think if you know it before, that'll make it better for me, because then you'll just kind of enjoy it. If you don't, I hope you'll at least get a little bit of the taste of what's going on with these various things. So the LCF was for Danish Scots Logical Computable Functions. And what is a logical computable function? In some sense, I don't need to say very much about it, because it really doesn't figure in some sense. Although it's an important logic, and I think it's much neglected, what the contribution of LCF was, what was the technology around it. But let's at least say what it is at a high level. It was just a type lambda calculus with recursion at any type, the famous Y combinator. And to axiomatize it, your atomic formula were less than or equal to, and you had a logic like a first order logic, and you had an induction principle for dealing with recursive definitions. So this is to say in a sentence what's actually several papers in huge correspondence, but I'm going to say everything in sentences like that. So what was the idea? The idea was to move away from theorem proving to proof assistance, to computer-assisted theorem proving. And the general thought there was, first of all, you knew what you wanted to prove. There's going to be a very large sort of thing, and you more or less knew the structure of the proof. And you didn't want to write down every detail, you wanted to produce the proof by composing together a number of proof strategies, try induction, if that doesn't work, generalize and do some simplifications, all that kind of thing. Those ideas weren't entirely new. Automath had this idea of machine help, and Carl Hewitt's planner had this idea of composing proof strategies, but one thing that this group did, which was completely novel, was to deal with the fact that these proofs are going to be gigantic as our systems get bigger and bigger. We really want to prove them. We need security to know that what we've proved is actually true, or at least provable in our proof system. And the way to do that is to have a programming language that lets you do that. And these ideas are enormously influential. Some systems, like Hall and Isabel, are direct descendants, other ones less so, others still less so in other traditions, but all of them use this kind of technology that Robin and his group produced first. So the idea is that you have 3 things in your programming language that help you achieve your task. The first one is abstract types, the second one, maybe a bit less important, is higher order functions, and the third one is exceptions. So in particular, you have an abstract type of theorems, and the only way you can construct a theorem is by using axioms or rules of your logic. So there's no way you can produce an element of type theorem unless the thing actually is a theorem. No matter what crazy programs you're doing, in the end, if it types a theorem, you've got a theorem. So this is a little bit of what the abstract type theorem is like. It has a theorem destructor, which takes a theorem and gives you a formula list in a form. Think of that as a sequence. An axiom to assume that it's given a formula, you get a theorem, given the formula phi, you get the sequence which says phi is true if phi is true, or w if w is true. And for rules, if I can prove phi 1 and phi 2, then I've got a proof of phi 1 and phi 2. Really the word theorem should be sort of proved sequent rather than theorem perhaps. And so notice you go from theorem to the sequent, but there's no function that takes you back from the sequent to the theorem, just straight out, which there can't be. That would be magic and illegal. How about tactics? How do they work? Well, a goal is such a sequence we're trying to prove. So a tactic says, given that sequence we're trying to prove, I'll return you another bunch of sequence that you have to prove. And this thing here, this proof, will say, well, once you give me a proof of each of these sequence, I'll give you a proof of the thing you first wanted to prove. So it's a kind of contract obligation fulfillment sort of cycle. So an example tactic is GenTac, for example. It says, you want to prove for all x something? Well, you give me a proof of phi of that something, phi of x for a fresh x, and I'll give you a proof of this, so obviously by universal generalization. But notice here, you might have been given an arbitrary sequence that might not be this formula form, because you might not be trying to prove a universal. So in that case, the thing will fail. You'll get an exception, a failure exception, and then some other tactic will be employed. And for example, and one has ways of composing tactics, so this OR tactic will exactly it'll do this tactic, but if that tactic raises a failure exception, it'll go on and try and do that tactic. So you can put things together like that using exceptions. So what I've done here, this is a list I put in deliberately. It's a list of a large number of people and several projects in the development of LCF. Actually, I was curious to notice that Whitfield Diffie, that was before he became famous. This one kind of became famous. Was on that list. Anyway, the point here is that Robin, to produce LCF in its various incarnations, many people combined. And this is one feature of Robin as a person. He could work very well with a large team. He was a very strong and persuasive leader, and he didn't persuade you by telling you what to do. He persuaded you because he'd worked with you one-to-one. And what you came to like together, that's the way things would go. And that's the way to be a leader. That's on being efficient. Many people have one quality without another quality. Robin had many such qualities. What happened with ML? Well, this is moving on to ML. As I say, it's originally developed with LCF. Then it became of interest. It just truly, maybe, I don't know if it's necessarily true, but anyway, what was good for theorem proving was good for anything, or even low-level system programming eventually. And so eventually one produced this serious language standard ML, which built on the original ideas and many other ideas. They have a list of the kinds of things that are in it, like pattern matching and polymorphism. These are new kinds of things. Abstract types, I said already, modules from Dave McQueen, various impure features. So two things I want to push on a little bit are that it was implicitly typed and in operational semantics. In the scheme of things, it's the first large-scale functional programming of successful one, or maybe at all, after Lisp. It had several influences. ISWIM, for example, Peter Landon, POP2, local people like Ron Burstall and Robin Popstone and Pope Burstall again. And it's had many successors: OCaml, Concurrent ML, Microsoft's F#, is it Martin Odersky's Scala, Java Generics, etc., etc. Haskell has been much influenced. It's part of the scheme of things, so to speak. It's there forever, ML, even if it never lives itself, its influences will always be there. Here's how implicit typing works. It's such a miracle for me when I first came across it. So here's the definition for function length. It takes a list and gives you the length of the list. But notice that its type isn't defined anywhere in the program. All we know is that, for example, the length given the empty list gives you 0. And given a non-empty list, it gives you 1 plus the length of this bit of the list. And here, later on, we take the length of a list of integers or natural numbers. Here we take the length of a list of booleans. So somehow or other, this is calculated. It comes out that the type of length is alpha list to int for any alpha, for any type alpha. And how is this miracle accomplished? It's actually by an algorithm previously known to others, but you can see how it works here. Think of length applied to the empty list. Well, length must have type beta, arrow, gamma since it's a function. The list must have type alpha list since it's a list. We don't know what alpha, beta, or gamma are. And the result of gamma must be int since this 0 is of type int. So therefore we know that gamma equals int and beta equals alpha list. So it's a very simple unification problem. We've solved it. And in this case, that gives you the type. Okay. Yeah, I can say more. About the operational semantics. This was actually quite late on in the development of operational semantics. So Robin and his team, Bob Parker and many other people, gave two things, static semantics and dynamic semantics. And static semantics says what the types of things are. If this is, for example, an exception handling mechanism. So you handle, here's some expression, if it returns a value, that's the value. If it raises an exception, you try to handle it with match. So if that's an expression of type sigma, match gives you something of type sigma. If you give it an exception, then that's well typed. Here's dynamic semantics. If the expression evaluates to value v, not raising an exception, then the whole expression with the handler also returns that value. Yeah, people haven't much followed the ML group in that respect. It's so much effort to give semantics a programming language. Perhaps one might recommend that they do, but it's easy to recommend other people do some work. Type soundness verifies that all of these things are working together correctly. That if an expression has a type, expression reduces to value, then the value has that type. And if I understood correctly, that has only recently been proved in the last couple of years by Bob Harper and other people at CMU. But it had been proved in many languages before. And in the original paper on type polymorphism is proof, I think, for a small language. Anyhow, again, a particular thing about what Robin did here, which was somehow universal for Robin, the way he thought generally about things. First of all, what you're doing should have some point. The language, or whatever it is you're inventing, should solve the practical problems that motivate its existence. That's condition one. Condition two, it should do so with an absolute minimum of concepts, or in Robin's case, an absolute minimum of beautiful concepts. And these concepts shouldn't just sit there, they should work together, they should have a good mathematics, and they should have good analysis, and that should lend itself, again, to useful application up there. So that was used again and again. So, it's not as... So this is now turning to some words about his work in semantics. This is a younger Robin, rather a darker one, working on operational semantics. And you can't quite see, this says that the meaning of a term m, if you apply it to a state, you get some other state, m, you get m prime. That's true if and only if when you symbolically evaluate it using operational semantics, p and n, some symbolic version of little m, you finish and you get to m prime corresponding to little m prime. This correspondence between denotational operational semantics is called adequacy, and this condition is a minimal condition. A maximal condition is behavioral equivalence. So let's say the operational behavior of a program is a set of pairs of states such if you start it off in the first, you get to the second, and say that two programs at any type, not just say low type, P and Q are behaviorally equivalent if for any context C of P has the same behavior as C of Q, that's the real equivalence that programmers are going to believe in for your programming language. And denotational semantics says that the denotation of them are the same if and only if they're the same operationally. That's the kind of goal that one can aim at. And this technique of this idea of full abstraction, which was actually Robin's name, but actually other people's idea, that Robin wrote some very important papers on it, about the semantics of LCN. This became a technique in his hands, and curiously enough, as a very important technique, and curiously enough it became a negative technique, which he turned to positive advantage. And why? What was going on for him? What was the problem he was trying to solve? So this was his secret, this was a so-called secret thought of Robin's, which was published in the Berger interview. He says, secretly I realized then I think it must have been sometime in Stanford, that working in verification automatic theorem proving wasn't getting to the heart of computation theory. It was Dana Scott's work that was getting to the heart of computation and the meaning of computation. I was concerned also to ask what the limits of computation may be. This interaction business began to seem to be breaking the mold, breaking the limits of what people had been trying to understand in a mathematical way, meaning domain theory, up to that point. So Robin had found some new fish to fry. He was going to solve concurrency or do concurrency. So he did start off doing it. He started off doing it in the tradition of domain theory. So this is the kind of thing you find yourself doing quite naturally, unnatural as it may seem. Oops. First of all, you think of something like transducers. You think of the behavior of transducers, you write down a domain equation for them. You say P equals this. So a process P, meaning the abstract entity corresponding to transducer, is something that can take in a value and give out a value at some address L. So you already had this idea of communication. He was concerned about concurrency as communication, not concurrency as shared store. That was the model he wanted to think about. And he already had addresses or things we're going to. So you can see precursors of things. So if you look, and he defined in his paper various parallel operators. So he defined an algebra of operators. So these are early ideas of input and output, communication, addresses, and operators were already there. But if you did something like this, first of all, it's very clunky. The programming language is pretty clunky. If you go into that, although it's right, it's clunky. And it's all wrong anyway, because you don't get the equations coming out that you want. So, and the equations that you want, we know what they are because they're given by the requirement of full abstraction. So you had to get working. So Robin entered his workshop, his intellectual workshop. I just wanted to mention what people don't know, which was also that he was a craftsman in the more intimate physical sense of the word. This is his workshop in his house in Cambridge. And there's a bunch of saws there, there's a bunch of chisels, a bunch of screwdrivers. This is where he worked. He was always working. I went to check some of my sources with Colin Sterling yesterday, and Colin said, oh yes, my blackboard eraser, he made my blackboard eraser for me. And many people have objects made by him, just as everyone has concepts. Anyway, it needed an awful lot of craftsman's-like effort to get from that early version to the later version. There's a long story which you can read, and I'll just, as it were, jump to the end. And where we got to in the end was a simple thing, a CCS, with a few core concepts, and really that was it. You could communicate some material for communicating. You could be in parallel, and you could have secret communication lines. I won't bother about these. You could define processes by recursion, and things were interestingly divided into two things. The red things Robin called dynamic operators. They were the things that made communication happen. Coming up to the end. Did we share 5 minutes?
Yeah.
5 minutes, yeah. And the static things were how things were arranged together. Robin gave an operational semantics based on label transitions relation. I thought that was a miracle because it was so simple to use. You'll see in a second how simple you can express concurrency with it. Given that, he defined an equivalence relation called bisimulation. Given that, he was able to specify concurrent systems by, roughly speaking, writing down a concurrent system, writing down another concurrent system which functioned as the specification of the first one, and proving them equivalent. It's odd for me, or maybe odd for all of us looking back, that although he did look at relations with a modal logic, he didn't apply that modal logic in any practical way. The link between the amalgam of CCS and model checking was only done later, and it wasn't a concern of Robin's. So when you take a bunch of processes and arrange them in parallel, Robin had a kind of pictorial or geometric way of writing these things down as flow graphs. So there's some agents, and they're connected by lines, you see, and there's some dynamic things in there saying what to do. This is actually somebody who asks his host for pineapple, who tells the servant to give the person pineapple. I want to point out this is not a quote from any Robin's papers, in case you think it's a very English kind of example of some sort. Anyway, the operational semantics, these are the kinds of rules you've got. If P can make an A move to P prime, and Q, and so that amounts to receiving a signal in the A line, and you can send a corresponding signal by Q on the A bar line, and P in parallel Q can make a move to P prime parallel Q prime with the silent move. So in one little line, one very simple rule, you get the semantics of concurrency, or the larger part of it. I thought that was a miracle when I saw it. A strong bisimulation is an easier thing to talk about than weak bisimulation, and that's the relation that they worked with. It's actually David Park who introduced this relation after some earlier ideas of Robin. And that just says that P can make a move, then it can be simulated by some move Q and vice versa. And so this notion of bisimulation, one of Robin's talents was to choose names well. This is by no means a talent to be despised, and it can be a talent that can be abused, but he used it well. And one of the names there was bisimulation. So there's a nice quote here that Robin, after David told him about this, they went for a walk, saying, what will we call this new thing? David said, oh, how about mimicry? And Robin said, that's difficult to say, let's call it bisimulation. And he said, well, that's got 5 syllables. And I said, it doesn't matter, people will be happy with it. And so you can decide if it was right or wrong. Okay, this slide just says that CCS had a lot of successors and a lot of influence and a lot of applications. I just want to point, having said that, the weakness, so to speak, or if you call it weakness, is that the communication architecture was static. How processes communicated was exactly given by the flow graph. That wasn't going to change. And in the days of mobile computation, that's not acceptable. So Robin invented the pi calculus, and I'm not going to have time to go through this, but it's Alice, Bob, and a new character called Charles. And Alice and Bob have a secret link X, and Alice happened to know how to talk to Charles, and she mistakenly trusts Bob, and using the communication link X tells Bob Charles's address, which then Bob immediately uses to tell Charles the secret communication link between Alice and Bob. This is a bad scene, but this is the kind of thing that one can do easily in the pi calculus that you couldn't possibly do in CCS, because communication links themselves are data that can be passed. Okay, and again, as with CCS, there was a very simple language for these things. The only difference really between this and CCS, between pi calculus and CCS, was you could actually send and receive channels. So for that reason, it became called X rather than A. So quite no differences between X and A. Anyhow, there's some technology there. And again, this has been a very successful language with very many applications. Security, for example, because it's, as an example pointed out, it's obviously connected to security. Many other applications. This is Benjamin Piercy's assessment of the pi calculus, slightly modified by me and others. So So it's not Benjamin's responsibility. He thought the calculus, this is for programming language people, he thinks the calculus is compelling in itself, a well-developed model of mobile computation, and basically that programming language people today have a stronger basis for concurrency distribution than they had 10 years ago, but we all do after the Pi calculus if we want to work with mobile computation. Yeah. Anyway, this wasn't enough for Robin. It wasn't general enough, so he went to work again. So here he is at work. It's a very characteristic Robin pose. He's leaning back, and once you're leaning back, you've got to put your head forwards, or else once you put your head forwards, you've got to lean back. I'm not quite sure, but this is him considering what just happened. And the question he's trying to answer was, could we get more general, usefully more general? And I'm just going to skip. So the answer was bigraphs. I think what I want to say about bigraphs is as you can tell, they have a double nature to them. One part is the place graph, the other part is the link graph. The place graph is a geometric notion. It tells you where things are, and you have locations inside locations inside locations. You have a forest hierarchy of locations. So these are the locations, these V's, and this is how they are sitting beside each other. But these V's also have agents at them, just as you saw agents in the flow graph. These agents can communicate with each other or have other links with each other, perhaps physical links. And these are described by a graph. Here's a hypergraph. Actually, the flow graph was also a hypergraph. In fact, it was a directed hypergraph. There's very little difference between these flow graphs, between normal flow graphs and this part of the bigraph. So you put them together as a single structure. And here's a little example, for example, from biology. So an obvious application of this is biology. Since you have many places in biology and you have many complex structures bound together and they tend to intertwingle, so how might that work? So you can see here, for example, there's a little membrane and you're budding off a little vesicle. The vesicle gets formed with these coat proteins. Once you're forming this little vesicle, this little chamber, the particles can diffuse into it and then the whole thing buds off and goes off to do its job, whatever that may be. And this would be a bigraphical reactive system to do that. It's worth pointing out what's happening here. So you see, here's a coat, here's the membrane, these are two places. Another place suddenly forms called the bud, and it's got a couple of agents inside it, they're connected, you have the coat outside. It's all very natural to write bigraphs and rules for bigraphs describing these things. Here, more coat proteins form a bigger bud. Here, you have diffusion reaction, and when there's enough of them, it goes off. It's almost like obvious, and that makes it wonderful. And it wasn't invented for this either, but it works perfect. Well, what would Robin have done next? He was very active up to, I saw him about a week or two before his death, with many other people. He was full of plans for the future. He was ready in Edinburgh, as I said. He was about to go off to Vienna, I can't remember, somewhere in Austria, to work on some institute to further his ideas on informatic systems. And so what kind of things was he interested in? He was interested in big problems like all this, so these ubiquitous computing systems, huge systems, today's internet, whatever gets bigger. He was going to work on that. He did have vast ambitions, and one might think him overblown, but he had a vast internal range. He would go from these vast ambitions to small concrete projects just to make an excellent step. But the point was to know where you were about to go. He understood how awful it was. He understood his idea was to look at certain sub-concepts and look for an ubiquitous abstract machine which would be based on a biographical calculus. I won't talk about that part. But as we unfortunately know, at that point he died. I think he was aware that he may not have had long to live. He said to himself that he might not be around to see what happened, but he was very curious to know what would happen. And he would still be very curious, and I am curious too. But I think that those ideas would although he's passed away, his ideas won't. And what he's done most recently, he began with algebra. The algebra stays there. He began to introduce geometry, and the two are beginning to fit together. And he made the connection with very important problems. I think there's a foundational contribution he's made there, and I think something will happen. And like him, I'm very curious to see what happens next. So thank you for your attention.
This production is copyright the University of Edinburgh.